Math 1332, Chapter 3, Symbolic Logic. Section 5, Euler Circles. Video 5, a third example using Euler circles. The first two examples were pretty straightforward. We could either set up the premises and it forced the conclusion to be true, or we could set up the premises in a way that denied the conclusion being true, making the argument invalid. But this one's going to be a little bit trickier because we really have to know what it means to represent a statement as opposed to not represent a statement. You'll see what I mean here in just a second. Also, this one is a lot more theoretical in the sense that we are not using specific sets but generic sets. Determine if the following argument is valid. Premise 1, sum A is B. So whatever A is, A could be eagles and B could be has wings. Some eagles have wings, but generically, sum A is B. Premise 2, sum A is not C. Conclusion, therefore, sum B is not C. Now we could replace A, B, and C with specifics, but that's the nice thing about abstraction is that you can remove the specificity from a situation and address it generically, so that way if the situation shows up again in a different context, you've already resolved the issue. All right, so we have three sets of objects as before, but they're very generic, set A, set B, and set C. So we're going to take the same approach as before. We're going to attempt to draw a Euler circle diagram that satisfies premise 1 and premise 2 and intentionally try to make it not satisfy the conclusion. If we succeed, the argument is invalid. But if we're forced to sketch a picture of the conclusion based on the two premises, then the argument is indeed valid. All right, so let's start with this first premise. Sum A is B. That is a particular affirmative, which means we have two overlapping circles with an X in the middle. So I've already got some circles set up here. Let's set up circle A and circle B. And we'll label them as such. Circle A, circle B. And to indicate the existence of sum A that is B, we need something representing an element in the intersection. So there is the Euler circle diagram for sum A is B. Now let's try to bring in the second premise, and this is where things get a little bit tricky. This is the first example where we've had more than one particular statement in the premises. Because when we draw, and here's why that's tricky. When we draw the Euler circle diagram for the first premise, we need to bring in an X to represent the existence of an element somewhere. But when we draw it for the second one, we don't have to necessarily use that same X. So we have one of two options. Number one, bring in another X, or number two, think about these Venn diagrams more like regions than just a single X in there. So I'm going to take out that X just for a moment, and I may leave it out for good. But when we say sum A is B, what we're basically saying is we have two circles that overlap, and their intersection is not empty. Something lives inside of there. I guess we can go ahead and put the X back in there, and we'll do that real quick. Let's take the font size down. All right. So really what we're saying is something lives inside that intersection. So let's think about the second premise. Sum A is not C. Now, if we ignore the second circle for a second, the B circle, because the second premise doesn't involve it, think about what it means for sum A is not C. That means the A and the C circles intersect somehow, and there exists something in the A circle, but not the C circle. Let's go ahead and call the circle C. Not you. So in other words, to say sum A is not C is the same as saying that was supposed to be a highlight, is the same as saying that this region is not empty. There would be anything in that region would belong to A but not C, so that would give us sum A is not C. How would we violate the second premise? which is like asking what's the negation of the second premise. Now, we haven't talked about the negation of quantified statements in a while, but the negation of some A is not C is every A is C. Raise your hand if you're in A, but you're not in C. Nobody raised their hand. Oh, I guess everyone in A is also in C. So in other words, to violate the second premise, we would have to have circle A. 1 second, folks. To violate the second premise, we would have to have circle A completely engulfed by circle C. Some A is not in C. Well, not according to this picture. According to this picture, every A is in C. So keep that in mind as we move forward. Let's bring back the B circle. I know it's here somewhere. There it is. All right. So for some A is not C, we need to make sure that circle A and circle C do not completely, let me rephrase that. We need to make sure that circle C does not completely contain circle A. It can overlap it. It can totally miss it. But if you'll notice, there's a lot of places I can put circle C relative to A and relative to B at the same time. For example, I could put circle C over here and clearly miss the B. I can't do this because then circle C would encapsulate circle A, violating the second premise. I can move it over here where it overlaps circle B, or if this circle were large enough, why is this not growing? Come on. The circle were large enough, there we go. If the C circle were large enough, it could also totally encapsulate B. So there's a lot of options on how to put circle C relative to circle A in terms of the second premise. The only thing we can't have is circle A completely inside of circle C, because then it would be impossible for the second premise to be true. So keep that in mind. We have a lot of places we can put circle C. We just can't put circle A inside of it. So let's move that out for a second. All right. Must the conclusion follow? Some B is not in C. How would we violate the conclusion? To violate the conclusion, well, it's just like violating the second premise. To violate the conclusion, we would have to have circle B completely inside of circle C. And I know I haven't labeled it C yet. It's because I'm moving it around. Let's get rid of circle A just for a second. Make sure we're clear on the fact that we just violated this premise. Get rid of this for a second too. That picture would violate the conclusion. I guess we don't need that highlighted part in the middle. That picture would violate the conclusion that some B is not in C. Really? Raise your hand if you're in circle B, but not in circle C. Nobody can raise their hand because circle B is completely contained inside of circle C. So this would violate the conclusion. Now let's bring everything back. Get the circle C out of there for a moment. Okay, so we've already got premise 1 set up, so I'm not worried about that. For premise 2, we need to bring in this circle and make sure it doesn't completely contain circle A. That would violate premise 2. To break the conclusion, we need to put circle B entirely inside of circle C. Can we satisfy the second premise and break the conclusion? The answer is yes. Keep grabbing that guy. There we go. He's not going anywhere anymore. All right, so let's take a look at this Euler circle diagram. Is premise 1 satisfied? Yes. Premise 1 involves circles A and B. Some A is in B. That's a particular affirmative, and we have that illustrated. So premise 1 is good. Is premise 2 satisfied? Some A is not in C. Well, let's get rid of circle B for a second. Some A is not in C. If you wanted to, we could put an X over here. I think we will. Let's bring back circle B for a second. If we wanted to, we could put some, we'll call it another X. It's just different X. And now let's get rid of circle B. And this X in the middle. It's not the one I wanted to get rid of. All right, just ignore the X in the middle. Have we illustrated premise 2? Yes. This X over here shows that some A is not in C. So we've got both premises satisfied. Must the conclusion follow? That some B is not in C. Well, let's get rid of circle A for a second. And this guy. Does this satisfy the conclusion? No. For some B to not be in C, B would have to escape circle C, but that didn't happen here. So this one was tricky because of all of the particular statements instead of the universals, but we have a picture that satisfies premise 1, sum A is B, that's the pink area with the X in the middle, and satisfies premise 2, sum A is not C, that's the X on the left, but the conclusion doesn't follow that sum B is not C. Every B is C, so there isn't one that's not. Although it's possible to draw the diagram in a way that illustrates the conclusion, it is also possible to draw the diagram in a way that does not illustrate the conclusion. Since the diagram for the premises does not force the diagram for the conclusion, the argument is invalid and you cannot draw that conclusion.